We'll do that. So if I go ahead and take the derivative of this, we're going to get 3x squared, right? Plus, now Joe said we have to chain rule that. So we really have to see it as y cubed, and then we've got the inner function y, right? So we've got plus 3y squared, so the derivative of the outer function, multiplied by y prime. And I'm just going to, you know what? No, I'm going to keep writing dy dx for a little while because I want us to really see that. Eventually, I would advocate you guys just write y prime. I think it'd be easier. And then Sarah said, well, we also need to be careful that -9, and that's a coefficient on what? Yeah, Abby, go ahead.
The xy, so it'll be the coefficient on the derivative of the product rule of xy.
Right, and so we need to be aware that we actually have to take the derivative of that product xy, so that's really what's going to go in here, right? And so when we go to product rule that, well, we know we're going to get, x times the derivative of y, right, which is just dy dx. And in this case, that's not so bad. Oh, that's going to be annoying. And then we also have plus y times the derivative of x, which is just, show me with fingers, 1. And so we're going to be good there. So I could put my multiply by 1. I don't need to. And all of this is going to equal 0, right? So why did we do all this? What were we trying to figure out? Come on.
Dy dx. What dy dx equals?
We're trying to get dy dx. We're still in that first phase of our plan, and sometimes having it written can really help us. So at this point in time, we really need to solve for dy dx, right? Because we want to get that type of equation up in there. So I'm going to go ahead and start collecting terms, maybe do some distribution. We're going to get 3x squared plus 3y squared and dy dx. Subtract 9x dy dx. Subtract 9y. And that all equals 0. Does anybody see anything nice that you would do at this point?
Would you divide by 3?
Yeah. Was that you, Judy?
Yeah.
Yeah. I noticed that there's a 3 in there too, and so I could make all of these numbers smaller if I just, got rid of a factor of 3 out of everything. You don't have to. You really don't have to, but it does make the numbers smaller. So if you notice that, it's not a bad step to take. So we'd end up with x squared plus y squared dy dx. Subtract 3x dy dx. Subtract 3y equals 0. So then how are we going to go from there?
Isolate the dy dx terms.
Yeah, let's get all the dy dx terms on that one side. Okay. We don't even need this. Well, I want to keep that. So let's get all the dy dx terms on one side. So I'm going to go ahead and move, or I'm going to leave these where they are, and I'm going to move these other two to the other side. So just doing some algebra. Sorry, my son's got class 2, but I think he's good. So what we'll get is y squared dy, I don't like where I wrote that. Y squared dy dx. Subtract 3x dy dx. All equals, that 3y is going to become positive and the x squared is going to become negative. I'm good, I'm not so good. Bonus. All right, and then we still need to isolate dy dx. How can we isolate that there? Somebody that's not talked. Come on.
You can factor out the dy dx.
Yeah, let's do that. So let's factor out that dy dx. And we'll have y squared minus 3x equals 3y minus x squared. And then we can just go ahead and divide, and we'll get what we wanted. So we're going to get more black space. And we will get dy, don't like where I'm writing it, dy dx equals 3y minus x squared all over y squared minus 3x. What questions do we have on that?
Where did the 3 go when we took it out of the equation?
You mean down there on that bottom line?
Yeah.
Well, Judy said we could just divide both sides by 3. So if you did that, if you think about dividing every single term by 3, you can see why it drops off on the left-hand side. And then on the right-hand side, what's 0 divided by 3?
It's 0, yeah.
Does that make sense?
Yeah.
Cool. Others? Okay, so let's get some more black space again, because we're not done yet. So great, we found this derivative, but what do we need to do now?
We need to figure out when dy of dx or dy dx equals 0.
Right. So we really need to set that thing equal to 0. So we really need to set 3y, and I'm going to write this out because if it was an AP question, I'd want to show my work, at least the big steps, right? All that other algebra wasn't necessarily big, but this, getting that derivative is big, and showing we're setting equal to 0 is big. What thoughts does that give you? Thumbs up once you have one. Fist in front of you means I'm thinking. Jana, what's it make you thinking? Make you thinking? I said that.
The top part when it equals 0.
Yeah, anytime we have a fractional structure that equals 0, Jen is saying we would know that this top, the numerator has to be 0. It's the only way you make a fraction 0. So that really helps us simplify it. And we can see, really, this is all we're worried about now. We're not worried about anything else. Which ultimately, how does that help us?
Can't we, move the x and then set it equal to y?
So something like that?
Yeah.
Just doing some algebra. I'm good with the algebra you did, Painter. I'm not so good. Okay, so all I did was added x squared to both sides and then divided by 3. Okay, so still, what does this mean for us? What does this mean for us? How many points, how many points could make this thing true?
Infinite.
Infinite. So in other words, there's an infinite number of points that could have a 0 slope, right? But there's actually not. Because at this point in time, we know that this has to be true. This has to be true about x and y. This must be true about x and y. So for x and y, to make dy dx equal 0. But is there anything else are there any other relationships that have to be true for x and y? I have a thought. I'm thinking. And the answer is right here. What we found was, a slope equation, right? So that thing up there, we were exploring the slope. This is what has to happen for the slope equation to give us what we want. But we still have to make sure that these points, these x and y pairs, we still have to make sure that those x and y's also fit this. Oh, wanted yellow. We still have to make sure that that fits. So we still need to make sure that the XY pairs fit with the original equation. What does this start to remind you of? What thoughts does this give you?
Substitution, maybe?
Which means you're starting to see it as what?
System of equations?
Right. So we've got our blue equation, because this is one thing we know, right? We know this about x's and y's. But then we've got this other thing, the original equation. We know that about our x's and y's too. And we really need both to be true. Does that make sense? So what I would encourage you to do at this point is go ahead but keep in mind we did get to a point where we had dy dx equals, what did we have real quick? Or no, sorry. We had y equals x cubed over 3, x squared.
Yeah.
And then we also knew that we wanted this original equation to be true as well. And so we had talked about substitution. When you substituted that, what did you end up getting? Nathan?
Okay, so when I put in that bad boy, I got to a point that essentially gave me an x cubed term an x cubed in every term. So I had x cubed plus x to the 6th over 27 minus 9x cubed over 3, or minus 3x is what I simplified that to.
Minus 3x cubed?
Yes, 3x cubed.
And that all equals 0?
Where we went from there was we just factored out an x cubed, and then that gave us x cubed times x cubed over 27 minus 3. So right away we knew that one of the x values that was going to give us a...
Pause right there.
You have to add the 1, so it'd be 1 plus.
Oh yeah, we forgot a 1.
So you
Right.
could just simplify that to minus 2. Yep.
Figure.
I'm with you. I'm not with you. Cool. So we did all this algebra. We're here. Keep going.
So right away we knew that since there's an x cubed term, that one of the ways that we will get a derivative of 0 is with the x value of 0. So basically, the way that we looked at that is one of those terms has to equal 0 in order for the derivative to be 0, in order for that to work. So the other term, we set that equal to 0, x cubed over, and then you can just move the 2 over to the other side and solve for x.
So that's a cube root of 54 down there. And so we got multiple x values. Right? Now, something we need to be mindful of, we would still need to get the y values. We're running out of time, so we're not going to do that fully right now. But we could, right? We definitely could do that. What questions do you guys have on any of the stuff we did? Because we did. This is a pretty tough problem, right? And that's okay. There's lots here that we group thought through. What questions, if any, do you have?
I have kind of just a minor algebra question. So in our middle term, when we substituted